All right, more 7.2. We're going to start by looking at what happens if you rotate things around lines besides the y-axis and the x-axis. So in other words, let's say we have a region like, let's make it fairly simple. Say we've got a horizontal line, we'll call that the g of x function, and then we've got an f of x function right here, and we want to take this region, this is the x-axis and the y-axis, and let's say we want to rotate that around the line y equals -1. In other words, we're not going to rotate it around the x-axis, we're going to rotate it around the line y equals -1. So the inside radius would be this distance, I would have that, and would get some kind of, I don't know how you want to describe this thing, but it's a big, hollow, gasket. That's what it is. It's a gasket. It's like this is the solid part, right? Alright, so it's like if we set it on the table here, it would look like, oops, right, this is hollow in here. Looks something like that. And this axis in the middle, that's that line, y equals -1. Okay, so if we weren't paying any attention to what we were rotating, if we were just rotating around the x-axis, then it would just be like what we did earlier in this section. We do pi times the integral from, let's say that's from a to b, wherever those are, a to b, of the outside radius, which would be f of x squared, minus the inside radius, which is that g of x squared dx. I left some room in there because how are we going to account for this? Well, it's basically like we could make this like it was rotating around the x-axis if we just shifted everything up one, right? If we shifted everything up one, then the y equals -1 line would be on top of the x-axis, and then it would be just like we never had to do any kind of new thing at all. So all we're going to do here is put that shift in. We're just going to shift everything up one, like that. But notice here that the +1 needs to be inside, right? Now, to do a problem like this by hand, it's going to be pretty messy, right? If you think about what that's going to look like. Usually, this kind of problem presents itself as a calculator problem, so you can just jam that all into your calculator, or a problem like you'll see some in the multiple choice practice, where they say which one of these represents the setup for this problem. So you just need to be able to set it up and not actually go any further than that. So that's how that works. The same thing goes with rotating around the x-axis, or a line parallel to the, parallel to the y-axis, I should say. So let's say we have a shape over here, and this is the line g of y equals whatever, and this is, notice I'm writing them as functions of y now because I'm going to rotate around here, and then this one could be some f of y, and let's say we wanted to rotate it around the line x equals 1, then that would be my inside radius, and I'd get something that looks kind of similar to this, right? Some hollow looking thing, right? Something sort of like that. And what would the integral look like? Well, if these were the numbers, our book uses the convention when they're talking about y numbers, they use c and d, and they use a and b for x numbers. So it would be the integral from c to d, pi times the outside radius is f of x, f of y, but I want to shift here. If I want to shift this way, I need to shift the opposite direction here. So notice that when we had y equals -1, I had to do a +1 here, and now for the line x equals 1, I want to shift it back to here, so that's like subtracting 1. I don't know what, oh yeah, minus the the g of y. And they're always going to have the same shift, like that. And I will point out one thing to you. Because this is being squared, this is the same as these are the same thing, right? Because f of y minus 1, whatever number that is, when you square it, you get the same number regardless of whether you do f of y minus 1 squared or 1 minus f of y squared. And I'm telling you this because it seems like in these set it up type problems from the College Board, for whatever reason, it seems like their answers more often come in this order, but it doesn't matter. You know, once you have it set up like this, just know that because you're squaring them and getting a positive number no matter what, the order doesn't matter. Okay? So that's how those work when you're rotating around a line that's not the x-axis or y-axis. You just have to apply a shift, and the sign of that number will change. That's all. Now, what if we design a solid in a different way? What if we take some area? These are much harder to draw, so you're going to have to bear with me. So let's say we take a region like our region from, well, let's say we have two curves here, a g curve and an f curve like this. So let's let that be the g of x curve and the f of x curve. And let's say they intersect at A and B. Sometimes you have to find those intersections, just like in 7-1, right? But that's not a big deal. Okay, and let's say instead of taking this thing and rotating it, let's say we're going to build a solid right here, right on top of this thing. And let's say that instead of being circular cross-sections, that every cross-section of this thing is going to be a square. So every little cross-section you can imagine, we're looking down on this solid, it comes up out of the page, and every single slice, if you put it through the Kroger meat slicer, this time instead of coming out to be little round slices, they come out to be squares. Every single cross-section of this thing is a square. So that's hard to picture, and I'm not going to try to draw the three-dimensional version of that. But I will ask you to please look in the book at some of their pictures of these things, because they've got nice little graphics in there. So what I'm going to do is I'm going to pull out a slice of this and say that this is that little base right here, and then I'll build the square up on top of that. So what's the area of this square? The area of the square, well, this side of the square is just the f function minus the g function, right? F of x minus g of x. The difference between those two, right? Just like in 7-1. So the area of the square is the side of the square squared. And if you want to find the volume, well, we have to add up all of these little squares, all of our slices, from A to B. And that's it. So these aren't really hard problems. You just have to figure out what that cross-section is and then draw a cross-section and figure out what your area is going to look like. Notice that there's no pi out here. Why not? Because it's a square, and the area of a square is just the side squared. There's no pi involved here. So unless they tell you that the cross-sections are semicircles or something to do with a circle, you're not going to end up with a pi in these questions. Oops, I forgot my squared there. Right? So let's do the same thing. We'll just do one more example with this. Let's say they said the cross-sections, each one of these is the base of an equilateral triangle. So now when I pull that out, each one of my cross-sections would be an equilateral triangle. Remember, that means that the sides are all the same length. So this would still be f of x minus g of x. But now how do I find the area of that triangle? Well, let's see. If you chop a equilateral triangle in half, it becomes two 30, 60, 90s. So this little piece, that would be half of this. And this, by your right triangle relationships that you know so well from geometry, your freshman year, only 3.5 years ago. This altitude would be half of this times the square root of 3. So the area is 1/2 of the base times the height, which is square root of 3 over 2 times f of x minus g of x. There's some geometry going on there for sure. And simplifying that a little bit, that's the square root of 3 over 4 times f of x minus g of x squared. And then what would our integral be? So the volume would be the integral from a to b of this expression. That's just a number, so like the pi's, I could take that to the outside, just like we do when we have a pi involved, of f of x minus g of x squared. So all the calculus part would be the same here. We just have that number on the outside. I'll tell you right now, they're not going to get harder than that. That's the hardest geometry you have to do. The College Board really likes squares, and they really like rectangles, where it's like, they say something like, it's 5 times taller than it is wide, which just means you get a 5 out there, like 5 squares stacked on top of each other. And that's really it. The tricky thing is just making a sketch and pulling that cross-section out. Once you've got that, it's pretty easy once you can get an area formula to set this up. And again, more often than not, these come up in the context of problems that you can do with your calculator or problems that where they just want you to set it up and they don't want you to go any further than that. So that's good news. All right, happy practicing.